and more energetically. This increases the chance that some molecules will be broken up into separate atoms, though the actual process is rather complicated. An oxygen atom might then strike a hydrogen molecule to form water, and more energy is given off than was absorbed from the match flame. The temperature goes up still higher, so that further breakup among the oxygen and hydrogen molecules is encouraged. This happens over and over again, so that in a very little time, the temperature is very high and the hydrogen and oxygen are combining to form water at an enormous rate. If a great deal of hydrogen and oxygen are well mixed to begin with, the rate of reaction is so great that an explosion occurs. Such a situation in which each reacting bit of the system adds energy to the system by its reaction and brings about more reactions like itself is called a chain reaction. Thus, a match flame put to one corner of a large sheet of paper will set that corner burning. The heat of the burning will ignite a neighboring portion of the sheet, and so on, till the entire sheet is burned. For that matter, a single smoldering cigarette end can serve to burn down an entire forest in a vastly destructive chain reaction. Electrons and energy. The discovery of the structure of the atom sharpened the understanding of chemical energy. In 1904, the German chemist Richard Abegg, 1869 to 1910, first suggested that atoms were held together through the transfer of electrons from one atom to another. To see how this worked, one began by noting that electrons in an atom existed in a series of shells. The innermost shell could hold only 2 electrons. The next shell could hold 8, the next 18, and so on. It turned out that some electron arrangements were more stable than others. If only the innermost shell contained electrons, and it were filled with the 2 electrons that were all it could hold, then that was a stable arrangement. If an atom contained electrons in more than one shell, and the outermost shell that held electrons held 8, that was a stable arrangement too. Thus the helium atom has 2 electrons only, filling the innermost shell, and that is so stable an arrangement that helium undergoes no chemical reactions at all. The neon atom has 10 electrons, 2 in the innermost shell and 8 in the next electron shell, and it does not react. The argon atom has 18 electrons, 2, 8, and 8, and it too is very stable. But what if an atom did not have its electron shell so neatly filled? The sodium atom has 11 electrons, 2, 8, and 1, while the fluorine atom has 9 electrons, 2, and 7. If the sodium atom passed one of its electrons to a fluorine atom, both would have the stable configuration of neon, 2 and 8. This, therefore, ought to have a great tendency to happen. If it did happen, though, the sodium atom minus 1 electron would have a unit positive charge and would be sodium plus, a positively charged ion. Fluorine with 1 electron in excess would become fluorine minus, a negatively charged ion. The 2 ions with opposite charges would cling together, since opposite charges attract, and thus the molecule of sodium fluoride would be formed. In 1916, the American chemist Gilbert Newton Lewis, 1875 to 1946, carried this notion farther. Atoms could cling together not only as a result of the outright transfer of 1 or more electrons, but through sharing pairs of electrons. This sharing could only take place if the atoms remained close neighbors, and it would take energy to pull them apart and break up the shared pool, just as it would take energy to pull 2 ions apart against the attraction of opposite charges. In this way, the vague notions of atoms clinging together in molecules and being forced apart gave way to a much more precise picture of electrons being transferred or shared. The electron shifts could be dealt with mathematically by a system that came to be called quantum mechanics, and chemistry was thus made a more exact science than it had ever been before. The energy of the sun. The most serious problem raised by the law of conservation of energy involved the sun. Until 1847, scientists did not question sunlight. The sun radiated vast quantities of energy, but that apparently was its nature, and was no more to be puzzled over than the fact that the earth rotated